So you might suspect that I changed the title due to these comments on incremental forming, but that was actually not the case. This change was decided by me some months ago when I realized that there were quite a few people experts in incremental forming, so I decided maybe I should talk about something else.
Right.
Okay. In Denmark, we have been working on trying to find alternatives to chlorinated paraffin oils for sheet metal forming since more than 15 years. We've had 3 large framework programs with Danish industry, lubricant manufacturers from Denmark, House in Denmark and Estica, as well as end users like Danfoss, Grundfos and Richard Müller. Later we had an EU project on the same subject with Shemeter as a lubricant manufacturer. Massa Oils is a Finnish company producing lubricants from fir tree. And again some end users like Mikelov from Spain and Konferanssı from Denmark. Maybe I should start talking about the chlorinated paraffin oils that, no, sorry, I think I'll go directly to the simulated trigo test. In these programs, we realized that we should make tests which would model the conditions in real industrial processes in a good way. Otherwise, you can get anything out of your testing, as you will see in some of our later results. Sheet metal forming is many things, and the number of simulative tests to model sheet metal forming are plentiful. This is a schematic drawing of a deep drawing, where you may model the conditions in the flange. We haven't shown the blank over here, by strip drawing between flat dies. You may have drawbeats, which can be modeled by drawbeat testing. You will have bending under tension in the die radius of curvature, and you may have ironing after the deep drawing operation. So, several tests are required for testing the lubricants since the conditions are so varied. We have chosen 3 simulative tests, namely bending under tension, drawbeat test, and the strip reduction test. The bending under tension has mild conditions with low normal pressures to medium normal pressures, low sliding length and low surface expansion. The drawbeat test is somewhat more severe with higher normal pressures, but still no surface expansion. And the strip reduction is really not a sheet forming, it's a bulk forming with surface expansion involved and bulk deformation. As process test, we chose deep drawing, ironing, and punching. And the first being a mild, the second a severe test, and the third a very severe test because you create virgin surfaces which are in direct contact with the punch stem, causing pickup. The major aim of testing is not to measure friction, but to test whether the lubricant can sustain the plastic deformation. This is a heavy redrawing operation from Mikelov with a good lubricant, and this is what we like to see with heavy scoring and bowling. As simulative test, we start with the bending under tension, where we use the principle developed by Weinmann, having thin wedges here as supports to this cradle. In the cradle we have a pin tool, and we have developed the test further. He measures only the vertical forces by strain gauges on these horizontal webs and the horizontal forces down here. But this requires for measuring a small quantity by subtracting a large measured force from a large measured force to get a small force. And we introduced a torque transducer for measuring the friction directly instead. We can preheat the tool pin to simulate the conditions in the production tool in deep drawing, typically up to 80 degrees. And here you see the influence of the temperature of the tool on, we have the front tension force here, the back tension force, which is constant, and then the torque, which is proportional to the friction. Testing stainless steel with plain mineral oil with no additives goes very well at 20 degrees. At 45 degrees the torque increased, but it's still working fine. But heating to 60 degrees you will see increasing torque and stick slip due to galling. At 70 degrees the lubricant breaks down immediately. Chlorinated paraffin oil works beautifully. That's the black one here. But we found other lubricants like the polymer coating, the yellow one, and the Pinifer, that is the fir tree oil based methyl ester, and they work just as good. The second test, draw bead test, is based on the same principle. Instead of doing the test twice here, we measure the friction directly by measuring the torque on the center roll. Normally you do the test twice with a rotating and a non-rotating roll here. But we use fixed rolls and measure the torque on the center roll by this piezoelectric torque transducer. We can heat the tools again, and if we run at room temperature for the tool, you see that all lubricants tested here works very fine, and actually the lowest friction is obtained with the pure mineral oil, that's the Houghton. Sorry, the colors are not shown here for some reason. But this is the plain mineral oil, the white curve. The heating to 80 degrees implies that all lubricants work fine again with somewhat higher friction, but still low, except for the plain mineral oil, which breaks down immediately. So the testing temperature is vital for the lubricant behavior. The third test is a strip reduction test, where we load the strip with a pin roll, a non-rotating tool, and then we draw it with a hydraulic cylinder to deform the strip in a strip reduction, similar to an ironing operation. This is a dedicated machine for this purpose. The tool pins here can be heated to maximum 200 degrees C by electric heaters, cartridges inserted in this loading tool. They have a square end surface in order not to rotate, and we can turn the tool 4 times, testing with the same tool surface, say 4 different lubricants, or repeat the test, and then know that we have exactly the same surface properties in the 4 tests. Evaluating of the test is done by roughness measurements across the strip with 30 millimeter interval, and you see that everything runs nice and smoothly until 210 millimeter sliding length, where you get breakdown of the lubricant and the first deep ridges, some micrometers deep. At further sliding we get heavy scalding. Testing of chlorinated oil goes fine. The mineral oil, that's the red one, breaks down, on stainless steel, and so does the fir-tree oil, whereas the polymer coating also works beautifully here. Coming to process tests, I'll only mention our punching test. So you see the punch being drawn automatically with a speed of 150 strokes per minute. And we measure the punch load as well as the backstroke force during test, as you'll see in a minute. This is one of the punches. There are two punches at the same time. You see the punch load and the much smaller backstroke force, and we take out the maximum backstroke force and plot here for each of the two punches, making two holes, to see how it develops. Looking at the punch load, for the first stroke, that's the two lowest curves with the triangles, the red and the black for the two punches. It increases and decreases to 0 when you penetrate the plate, and when you withdraw the punches, there is no backstroke force. But at stroke number 1600, you see a vast increase in the backstroke force. This is due to pickup of workpiece material on the punch stem. And this pickup develops quite gradually. You see how gradually from the first stroke the backstroke force increases, here for chlorinated paraffin oil, here for plain mineral oil, and the scale here is 3 times as large, so the backstroke force for plain mineral oil is much heavier. Testing different lubricants, like no lubricant, the maximum backstroke force increases heavily with the number of strokes, and so it does with dry-in lubricants, since the lubricant cannot get access to the punch stem. A polymer coating is also a poor lubricant, giving high backstroke force. Low viscosity oil doesn't work at all. A high viscosity oil works somewhat because it adheres to the punch surface, but not very well. Whereas the chlorinated paraffin oil works beautifully. So we can clearly distinguish the different oils. Other lubricants, however, also work, like the Pinifer oil. And we realized that the reason for the Pinifer oil to work was not heavy viscosity, it's not very highly viscous, but the fact that it reacts with the punch material. So the mechanism of lubrication in fine blanking and punching operations is that the lubricant forms a boundary film with the tool material. This was proven by making differential thermal analysis of the reaction between the oil and the punch material in powder form. And we showed clearly reactions from the chlorinated oil with the punch material and for the Pinifer oil. So here we have to design the lubricant not to work with the workpiece material but with the tool material. An idea which has not really been played upon earlier. We did end users tests with several of our co-workers, among these Konferansı in Denmark, producing stainless steel pumps. And there we tested in a progressive tool of forming this cap, punch cap, from punching, deep drawing, and punching again here, and then a color drawing combined with an ironing operation of heavy reduction, 30%. That's shown in detail up here. And finally blanking the component. It's process number 4 which is critical. If you use a bad lubricant, you see you get scoring of the workpiece and galling. We did tests of different lubricants, different reduction speeds, and different workpiece materials, and we measured the backstroke force and the tool temperature in this critical operation. The temperature was measured by mounting thermocouples close to the contact interface from behind, 1 millimeter from the surface, in the punch as well as the die. And you see the development of the punch temperature. The simulated temperature development is here, and the measured is also undulating, but here shown in mean value so that we can distinguish them. If you run with 100 strokes per minute, you see an increased temperature, of course. We simulate the temperature development in the punch with the number of strokes, and here you see how fast it actually develops to steady state. Within 2 minutes, the temperature is constant. And you see how heavy influence the speed of production has on the maximum temperature. This is the tool workpiece interface temperature calculated by FEM. If we come up to 110 degrees, we have experienced that the lubricant fails. We found that one lubricant from Rayner's, a mineral oil with calcium, phosphor, and sulfur additives with a rather large viscosity, together with the titanium aluminum nitride coated punch, worked very well, and we could produce 10,000 components at maximum production speed without galling. Here you see the temperature development in deform, but I think I will not carry on here. It takes a while to get to equilibrium. So this is not the conclusion of the paper, but the conclusion of the first part, and I have a small second part. Temperature development to steady state occurs within a couple of minutes. And the final level is independent of the lubricant, almost, but highly dependent on the production speed. The calculations fit with measured temperatures, and onset of galling may be done sometimes by temperature increase. We can see that when galling occurs, the local temperature increases strongly, but it's only when the thermocouples are in the neighborhood of the galling. So it could be anywhere around the periphery, and therefore not a feasible way. But we can measure onset of galling very clearly by measuring the backstroke force, even in production tools. So one can stop before the galling gets severe. Low production speed can prevent galling, which may appear if you use twice the speed. And galling is more pronounced in IC 316 than IC 304. There are large advantages in offline testing of limits of lubrication in order to avoid production stops. It's very costly to do the test in production, and the lubricant manufacturers are overrun by people who want them to test their wonder lubricants, and this gives a lot of headaches, which we can solve by doing it in the laboratory. And the test systems we have developed seems to work well to model the conditions in industry. It's vital to test at elevated temperature to model the real conditions in production. And we found a number of environmental friendly lubricants which works fine for deep drawing. I have just 3 slides more. Polymer coating proved very well for single-stage production, but in multi-stage it's no good, we found. And Grundfos had really relied on using this lubricant but had to abandon it, since when you do multi-stage lubrication, it doesn't work. But then some of the environmental friendly oils, together with coated punch, work very good. But the best lubricant is still chlorinated paraffin oils. And for this case, we have started a new project together with Swedish industry and Grundfos, Uddeholm, Swedish Steel and Outokumpu Stainless in Sweden are paying the building of a new triple tester. The one we have is now 20 years old, so it's about time we get a new and much more advanced tester. I want to say a few words about lubricants for co-forging, because I think there are some co-forgers here. And there has been quite interesting development in the latest years regarding co-forging lubricants. In co-forging, you also have environmental problems using zinc phosphate coatings, which gives sludge of heavy metal phosphates which have to be buried, disposed by burying, and it's costly to renovate your baths and so on. It's also a lengthy procedure, and all these things have motivated lubricant manufacturers to try and find alternatives. And there are many alternatives which are not working especially well, but work for lighter co-forging operations. However, it seems that Nihon Parker Rising in Japan has found the secret, you could say. They have developed a new lubricant system called Parker Ultimate Lubrication System. In Europe, it's marketed by Henkel, called Bondelube Fine Loop, I think. And it reduces the number of operations from 9 to 4. In normal phosphate coating and soap lubrication, you take 24 minutes to coat, and it has to be offline. In the new process with Pulse, you descale the workpieces by shot blasting, you heat them, you coat them 40 to 60 degrees for 1 second, and then you go. You dry them and then you forge. And you could do it in process. So it's a total of 3 minutes to coat them, and Nihon Parker Rising claims it to be very efficient. I have another slide with that. We cannot get the complete secret, but it is similar to phosphate coating in the fact that salt is reacted on the metal surface and bonded to the surface, and on top of that we have an organic film, and it's much like the phosphate coating and soap lubrication. Here are some examples on co-forged products with this new technology. And this is what Nihon Parker Rising claims. You have a diagram here showing components made by low to high surface expansion, from short to long sliding lengths, forging bevel gears with high surface expansion and spiders, and forging long axles, transmission shafts. And this is the limit of lubrication for soap phosphating and phosphate coating and soap, and Pulse is claimed to have almost the same properties. I know a similar diagram by Toyota looks like this, and this is already introduced in production, but they do the same components on trial at the moment. So that's what I had to say.
Well, I would like to take on your behalf both Professor Bai for his very extensive presentation on an important subject like friction in metal forming. We know it's one of the very difficult parameters to find out for theoretical simulations and evaluations of lubricants and so on. So let us invite your questions and comments. First, Paranatha.
I just want to add that Daido and Hymet also developed similar lubricants, and I believe Toyota is using the Hymet. And this is also marketed in North America also.
They also use the Homet. I think it's a
Hymet or Homet or something like that, yeah.
Yeah, but it's not so good as Pulse, as far as I know.
Well, we checked them. We checked all four of them.
Yeah, I know you checked.
And you can see
but
my results.
You haven't checked Pulse. I don't think you've checked Pulse.
No, we didn't check Pulse.
No.
And they were better than Pulse coating.
Yeah.
They were better than Pulse coating.
Right. Other questions and comments? Let me ask a quick one. Sorry, please. Proceed. Okay. You had a drawbeat test you showed us at the first part of the presentation, and you measured the torque to find the friction coefficient. Now, in such cases, do you find that the friction coefficient or friction torque has a high value and then there's a decrease when it starts to turn? That means the difference between static and dynamic friction.
But we don't turn.
You
you mean when it starts to slide?
Yes, slide.
But we don't turn,
Okay,
We keep the roll fixed. It's a similar setup to the bending and the tension, where the pin is layered in a cradle, and the cradle is layered in needle bearings, but it cannot rotate due to the torque transducer. So we measure the torque, and it's the same in the drawbeat test. Yes, we have difference between static and dynamic friction. Yes, it's higher, typically higher the static friction.
Thank you. And proceed. Okay. Other questions, comments? Well, I think we hope to see the days in which we can find the friction coefficient distribution on the contact areas. And I think Professor Roll also indicated in one of his slides, this morning, that there is such a need, but still we are short of some techniques of evaluating friction coefficient distribution over the contact surfaces.
For sure. Especially in sheet forming, it's extremely difficult because the lubrication mechanisms are so varied. I should say one of the best ways to solve it may be to avoid using lubricant, like if you can invent coatings where you don't use lubricant, then you are more sure of your friction. And Japanese have developed a diamond coating which works for deep drawing without lubrication, and that looks promising.
Also,
boride coating, if it's oxidized, then boride oxide nucleated. If there is moisture in the medium, so that you may get boric acid, which makes almost close to zero friction coefficient.
Yes? Okay. I'm sure there are several good solutions which we don't know about yet, which we have to... Yeah, but I have no doubt.
Yeah. Okay. Well, again, I'd like to thank Professor Bai and all the other authors who have made excellent presentation, and to all the participants who have attended this session.